Welcome to section 9.4. In the previous sections, we introduced the concept of solving systems of linear differential equations, and we are looking at how to actually solve those systems now. We also looked at the very end, in the last section, at the general form that we can apply to these solutions. So here we're going to look at this form again and actually start solving some problems with it. So in 9.4, we're looking specifically at the case where we're solving vector differential equations with a non-defective coefficient matrix, because we need eigenvalues and eigenvectors to be able to come up with these solutions. So we're looking at the case where we have a non-defective matrix first. So if A is non-defective, we get n Li eigenvectors, v1 through vn for A. So we can form n solutions for lambda 1 through lambda n. So that's these solutions right here. So we have x1 is e to the lambda 1t times v1, x2 e to the lambda 2t, v2, etc., etc., etc. Now, if we were to take the Wronskian of these solutions, so we take the determinant of the x1 solutions, the x2 solutions, etc., etc., and augment those into the columns of a matrix, what we can do is we can take all of these coefficients on the vectors and pull all of those out, column by column. That gives us this expression times the determinant of all of the v vectors, all those eigenvectors. This expression here, any value of t will keep this non-zero because you can never turn this exponential function into a zero. So this is always non-zero. And this determinant with these vectors v1 through vn, this will also be non-zero since the columns are Li. All right, and that's what we assumed right here, that it's n Li eigenvectors. So we have a non-zero expression times a non-zero expression, so that whole thing will be non-zero. So what that allows us to conclude, so we can say, so these solutions are Li. So we do have a set, x1 through xn is a set of Li solutions. So our general solution is going to be some linear combination of all of these individual solutions. So we're going to get x of t is c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2, etc., all the way up through cn e to the lambda n t vn. So this will be our general solution to systems of this form. Okay, we're still dealing with the homogeneous systems here, so no plus b on these terms. Let's take a look at an example. So find the general solution to x prime equals this 2 by 2 matrix, -2, -7, -1, 4 times x. So note, we give them in the vector and matrix form here. This is our more condensed form, but this is the same thing as this system of differential equations here. So x1 prime equals -2x1 minus 7x2, and x2 prime is -x1 plus 4x2, right? So if you do the matrix multiplication with the vector x with x1 and x2, that's what you get. So we are solving a system of equations here, even if it doesn't quite look like that in this current form. But we need to find the eigenvalues and the corresponding eigenvectors. So we're going to get the determinant of a minus lambda I, so -2 minus lambda, -7, -1, and 4 minus lambda. So we'll get negative 2 minus lambda times 4 minus lambda minus 7, negative 7 times negative 1, so it's just minus 7. And we're going to set that equal to 0. FOIL this out, combine with the constant, we end up getting a lambda squared minus 2 lambda minus 15 equals 0, which is factorable. So we get lambda minus 5 and lambda minus 3. So we get lambda is 5 and 3. So those are our eigenvalues for this matrix. So we need to get the corresponding eigenvectors. So we have lambda 1 will be 5. So we take the null space of a minus 5i, so subtract off 5 for lambda. It's negative 7, negative 7, negative 1, negative 1. With the null space, we perform some EROs here, so I would, maybe move this one to the top, make it 1 and 1. The other row is a multiple of the first, so that's a 0 and a 0. And with the null space, we augment with the 0 vector. So we've got our pivot right there. This gives us our corresponding eigenvector. So like this would be the free variable t, this would be negative t. So we're going to get negative 1, 1 for our eigenvector. So our first solution, so x1 of t, remember they have this form. So e to the lambda 1t v1. So that's going to be e to the 5t times negative 1, 1, that vector. Okay, so that's our first solution. Then for lambda 2, so we have 3. So we take null space, subtract off the 3, we get negative 5, negative 7. And we get, oh, did I mess up that value? Yes, I did. Have you been yelling at your screen this whole time that I messed up that factorization? This should be lambda plus 3. So that should be negative 3. Yeah. That's better. So that's negative 3. So that's negative 2 minus negative 3, so that's 1. There we go. Okay, that is better. So now, let's see, we get negative 1, 4 minus negative 3, so that's 7. So 1, negative 7, that's going to cancel that row entirely. Augmented with 0 vector. So we get, this is the free variable t, and that's going to become 7t when you solve it. So that's 7 and 1. So x2 of t is going to be e to the negative 3t times the vector 7, 1. And that's going to be our second solution. So for our general solution, we're going to get x of t is c1 x1 plus c2 x2. So c1 e to the 5t negative 1, 1 plus c2 e to the negative 3t 7, 1. And that will be our general solution to that system of differential equations. And note down here at the bottom of the page, if there was an initial condition given, so like x of 0, for example, we could solve for C1 and C2, given that value for t. We saw an example like that last time, but of course, in this particular problem, it's not asking us for that. Next up, we're going to take a look at how we handle complex values within our solutions. So let u of t and v of t be real valued vector functions. If w1 is equal to u plus iv and w2 is equal to u minus iv, so we have complex conjugate solutions. Okay, so these w1 and w2 are both solutions, but they are complex. Then x1 can be u of t, and x2 will be v of t. They are themselves real valued solutions of that system. So what this is telling us is if we go through this process of finding eigenvalues and eigenvectors, we end up getting complex solutions for these, for the system. Instead of using the full complex solutions, we can take the pieces, the real piece and the coefficient on the imaginary piece, and use those as the solutions themselves instead of using the complex versions. Okay, so this allows us to then solve these problems using complex values, but get real valued solutions. Okay, so we can avoid complex solutions to these systems. So for this one, find the general solution to this system. We got a 3x3 matrix here. I went ahead and already set up the determinant of a minus lambda I and found it, and then it factored already. So we get lambda is 5 and lambda is plus or minus I. So if we start looking at the eigenvalues, we'll get those corresponding eigenvectors. So lambda 1 will be 5. So we get null space of -5, 1, 0, -1, -5, 0, 0, 0, 0. If we move things around a little bit and row reduce, so like we can make this the top row, so like 1, 5, 0. And then that 1 will get rid of that 5, and then the other one simplifies to a 1, and the bottom row is all zeros. So we end up with one free variable, but the way that this works out, the free variable ends up having no impact on the first two, right? This equation here tells us that the second value is 0, which makes the first value 0. So this vector is 0, 0, 1. So we get our first solution, x1 of t, that's e to the 5t times 0, 0, 1. Okay, so that's our first solution. That's our more straightforward solution, because now we're going to look at the complex ones. So we have null space, -I, 1, 0, -1, -I, 0, 0, 0, 5 minus I. So what ends up happening when we do row reductions on this, one of these rows will get rid of the other, and you can check that independently, but we'll end up with 1I 0. And then this one, we can just, this is all constant. We can just multiply by 1 over 5 minus I and switch that up here. So we get 0, 0, 1. And then our all 0 row goes at the bottom. So that puts it in row echelon form. So our V2 is going to be, we have a 0 in the third component. We have our free variable here, and then a negative I times the free variable here. So negative I, 1, 0. So the kind of the starting form that we would get out of this, we would get e to the it times negative I, 1, 0. And if that value wasn't complex, that's all that we would need to do. That would be our solution. But we don't want a complex solution. We want a real valued solution. So we need to mess around with this a little bit. Luckily, we have the tools to be able to do this. So for e to the it, that expression, we can use Euler's formula to rewrite this. So this is going to be, get a little more room here. So x2 of t. That's going to be cosine of t plus I sine of t. So that is this because of Euler's formula. And then for the vector here, I'm going to break apart the real valued components and the imaginary components. So this is 0, 1, 0. Pull out the negative I, so minus I times 1, 0, 0. Now if we regroup, so if we basically just FOIL this out, so right, first, outer, inner, last, something like that. Distribute everything, you'll get some terms pick up i's, some terms cancel i's. But when all is said and done, so we end up with cosine of t, 0, 1, 0. We get plus sine of t, 1, 0, 0. That's because we multiplied these two. We have an I and a negative I. I times I is negative 1, so that makes it a positive. So we're just left with sine times the vector. So let me move this. So we get then plus the other components will be times I. So that would be the outer and the inner, where you get the I popping up on there. So that's going to be negative cosine of t times 1, 0, 0 plus sine of t times 0, 1, 0. So what we have here now is this form of like a plus bi kind of thing. But if we look back here, that is this, right? U of t plus I v of t. So instead of using this whole thing as one solution, we're going to use these two separate pieces as two separate solutions. So these will be our solutions. Now, if we look at what happens with lambda 3, because we know if I is an eigenvalue, negative I will also be an eigenvalue, but we also know how the form matches, so we don't have to go through the null space again. We know that it'll just give us that complex conjugate. So we get I10 instead of negative I10. which would give us x3 would be e to the negative it times I10. So if we approach this one the same way that we approached this one, we end up getting x3 of t is cosine of t 0, 1, 0 plus sine of t 1, 0, 0. We get minus I negative cosine t 1, 0, 0 plus sine t 0, 1, 0. Right, so we end up getting the complex conjugate of this one, right? We had this plus I times that, and then we had this one minus I times that. But even though these are complex conjugates, the pieces, like that u of t and v of t, they're the same for both. So we get same solutions. So this step is unnecessary. We don't have to worry about finding the solutions for the complex conjugate because it will ultimately provide the same solutions. So now we're going to rename our solutions here, because technically if we were going by the terminology up at the beginning, this one should have been like W1 and this one should have been W2, like that. So what we'll do is we'll just rename x2 and x3. Instead of making x2 this whole thing and x3 this whole thing, we'll call this x2 and this x3. So the different components. So x2 will be cosine of t times 0, 1, 0 plus sine of t 1, 0, 0. And x3 will be negative cosine of t times 1, 0, 0 plus sine of t times 0, 1, 0. So these will be our other solutions. Right? So we have a 3 by 3 matrix back up here at the top. Right? 3 by 3 matrix, it's non-defective. Each eigenvalue produced one eigenvector. And now our general solution will just be the linear combination of x1, x2, and x3. So our general solution, so x of t, so it's c1x1 plus c2x2 plus c3x3, so that's c1 e to the 5t times 0, 0, 1 plus c2 times this whole expression for x2, sine of t 1, 0, 0 plus c3 times the whole expression for x3. So this gives us our general solution right there. So as you can see with these types of problems, we are definitely getting longer, more expansive examples and solutions to these types of things because we're solving much bigger and bigger problems. We're solving not just single differential equations, but systems of multiple differential equations, and so the solutions to those systems can get pretty complex, no pun intended, especially when there are complex values involved in the calculation. So this process that we go through here, we can use this process and like derive it every single time, but we also develop a formula for this just in general. So if we want to use this instead, we absolutely can. So for complex eigenvalues, a plus b plus or minus bi, the eigenvectors that we get would be r plus is, or r plus or minus is. So we can derive solutions for x1 and x2, and they would be e to the at cosine of btr minus sine of bts, and e to the at sine of btr plus cosine of bts. So if we know the eigenvalues and the eigenvectors, then we can just jump straight into these forms for our solutions. And that's going to simplify our work a bit and not make us kind of derive the process every single time using Euler's formula. So let's take a look at an example with that. You can see I already got a little bit of a head start on this one. So find the general solution to this system of differential equations. So I went ahead and set up determinant of a minus lambda I. So we multiply that out, expand, and this one does produce only two complex eigenvalues, so no real numbered eigenvalues here. So if we look at lambda equals 4 plus 2i, we take null space. That ends up giving us, so 5 minus 2i, 29 over here, negative 1 here, and negative 5 minus 2i down here. Working through the row reductions here. So we'll move the 1 and the 5 plus 2i up here. And then this row will end up canceling and turning all into zeros. So our eigenvector, we get a 1 here for the free variable and then subtract this over. So we get negative 5 minus 2i and 1 for our eigenvector, which we'll go ahead and break up into its real and imaginary components. So that's negative 5, 1 plus I with negative 2 and 0. So we know that with this eigenvalue eigenvector pair, we could find like the complex conjugate, the 4 minus 2i, but it would end up just giving us the complex conjugate of all of these same things, and it wouldn't contribute any new solutions to the problem. Now we can set this one up like we did the last one if we wanted to, and we could set it up in its general form, use Euler's formula and do the foiling and the multiplication and combine the complex terms with the real terms, and then extract those two pieces from the solution, all like we did in the last one. Or we can instead use these forms of the solution, and you will get exactly the same thing. So we already know A and B and R and S, and that's all we need to be able to set them up this way. So our x1 of t is going to be e to the 4t, that's e to the at, cosine of bt, so b in this case is 2, So cosine of 2t times r, so that's the real valued vector, so negative 5, 1, minus sine of 2t times the imaginary vector, so negative 2, 0. We don't need the I itself, we just need the vector that is attached to the I. And that's, again, the benefit of this process, is our solution will be all real numbered, no complex values. So we could leave it like this in this form, or we can also try to kind of recombine all of this stuff to condense a little bit, consolidate. So we get e to the 4t times negative 5 cosine of 2t plus 2 sine of 2t. And we would get down here just cosine of 2t for the second component. So that would be x1. And x2 is e to the 4t cosine of 2t negative 2, 0 plus sine of 2t negative 5, 1. In the formula back on the last page, it has them switched, but I don't know. I like to have the consistency of cosine coming first and sine coming second. It doesn't really matter, though. You could switch them around, and it's all the same thing. So we get e to the 4t. If we were to consolidate, that would give us negative 2 cosine of 2t minus 5 sine of 2t. And down here, we would just get sine of 2t. So our general solution is just the linear combination of these two. So x of t is c1 e to the 4t times this plus c2 e to the 4t with that second vector right there. Let me move this whole thing over just a tad. There we go. So this is our general solution. So again, this tactic does allow us to solve problems with complex eigenvalues and eigenvectors and still somehow produce real valued solutions, which is a very important tool for us. Again, using Euler's formula that allows us to then derive this simpler process for solving these systems. But that brings us to the end of section 9.4 at our look at solving these systems of differential equations with a non-defective coefficient matrix A. We'll see in the upcoming section what happens when our coefficient matrix is defective.